Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very interesting lead code problem, longest common subsequence, and unlike many other interview questions, this actually is a very good problem to solve because it does have real life use cases which almost all computer engineers use on a daily basis. Basically, GitHub is one of the prime example that uses the solution of longest common subsequence in its functionality. This is going to be a really long video because I want to make sure that I be as thorough with my thought process as I can, and that is why I have decided to break this video in different chunks. So if you are comfortable, feel free to directly jump to that portion, and this is the approach we are going to take. We'll understand the lead code problem. We are going to come up with a primitive solution using recursion. Then we will see that how can we use memoization to improvise on the recursive part, and then we are going to see that how can we use dynamic programming to get the optimal solution. And basically once we have the optimal solution, we are going to write the Java code for it. So let's understand the problem. In order to understand the problem, first we have to understand a very key factor, that what is a subsequence. Basically, if any value is given, suppose we are given a string a is equal to x, y, and z. A subsequence is any elements that are present in this given sequence, though they might be out of order. So x, z is a subsequence, y, z is a subsequence, y by itself is a subsequence. But if we consider like yx, this is not a subsequence, because if you see the order in which they are represented over here is not the order in which they are represented over here. So just keep in mind. And now once we have it clear that what a subsequence is, let's understand the problem statement. So we are given two strings, text1 and text2, and we need to return the length of their longest common subsequence. And if there is no longest common subsequence, we just return 0. So let's take it by an example that is given over here. So if our A is A, B, C, D, and E, and B is A, C, and E. So now we need to find the longest common subsequence. It's pretty simple that if we just draw the lines, we can determine that A is present in both the cases. C is also present and E is also present. And notice that there exists this B and D, but if we remove this B and D, basically A, C, and E will remain same in for both the strings. So we can say that A, C, and E are a subsequence that is present in both the places, and we want to return their length. So in this case, the length would be 3. See that what should be the most primitive approach to solve this problem. Once we understand that, we are going to make improvements to it, and based on the improvements we are going to come up with the optimal solution. So basically most simple thing that you are going to do is compare every single element with every single other element, keep on doing it, and whenever you find a match, do something else. So let's see that what should be the approach. We will start by checking all the elements from first element to this element in the B. We don't find any match. Okay, we move on to the next one. Okay, now again we do the same thing. Over here we find a match. The moment we find a match, now we need to find the longest common subsequence. The way we are going to find longest common subsequence is only by eliminating whatever we have calculated so far. So the thing is, now the area of calculation that we are going to achieve is actually limited to up until this point and up until these points on the B side. And the reason we are going to do the reason we have to do is because if we don't do it, if we just move on to the next element, basically we are going to lose that connection that we have made at this point A, and we need to find the longest common subsequence. So after this my long speech, let's see that what should be the way forward. Now we again start comparing with C, but now we are only going to compare with these three values. So C to I, no match; C to X, again no match; C to B, again no match. So we don't find any value over here. Again we repeat the same process for this K. So again there is no match. But now when we come to this I, yes, we find a match. And when we find a match, we repeat the same process. So the process is that now the area of a search that we have to perform on the first string, and on the second string we only have these two elements that we need to consider. So let's do the same thing. Compare e with x, nothing, and e with b, nothing. So we have found something. The thing is, we cannot stop right here because there could be a potential better substring that was not caught over here, but it might very well be hiding somewhere later in the picture. So what we do so far, we store the value whatever we have calculated over here, and the substring we have calculated so far is of length 2. The values are a and I, and now once we have this value, we'll again repeat the same process that we were doing. Now we will again check with the C with all the other values of this B substring. So we find a match over here at C, which means again the area of interest reduces. Now we only need to check for these three values, and we only need to check for these values on the lower substring. And when we do that, let's repeat the same process. And so far we have found one common element, so we can put one as common element. And now we jump to the next elements. When we jump to the next element, this k, okay, again we found a match, so we do 1 plus 1. Our area of interest again shrinks down. Now it shrinks down to only these 4 elements on the bottom string and only these 2 elements on the top string. Again we repeat the same process. We check with I, we don't find anything. We check with I, yes, we find something. Once we have found over here, so we do addition over here again, and now our area of interest again shrinks down to only this element and only these 2 elements. Again we do the check, and yeah, we don't find anything. So far the longest substring we have found is actually 3. We compare 2 to the 3. Okay, 3 is greater, so we are keeping 3 so far. But the thing is, we are not done yet. We are not out of the woods yet. We'll have to check for all the other remaining values as well. So what would be the remaining values? So far we have checked until this J, A and C. Now we again repeat the same process from this K. Okay, K to K, there is a match. Again we will find K to I, there is a match. The longest common substring we have made so far is only 2, but 3 we already have a better substring, so let's keep it on the side. Now we have calculated the values for K. Now again let's repeat the same process. Again with I, we compare all the values. Okay, we find the substring over here from this value I. Again this is only 1, and we don't find any other values, so we are done. Now we are at the last element E, and again we check with all the values of B, and we don't find any substring, so we are done over here basically. And this is the most primitive approach. Now let's try to see that based on this we have found 3 conditions so far, and using these 3 conditions, the most common algorithm we can write is a recursive one. I mean, you can write an iterative algorithm as well, but recursive is just less code, and I have already written that for you. So let's go over the algorithm. We have 3 conditions. First condition is at any point if we reach the null value, we can't return anything, so we return 0 basically. This is our terminating case, and eventually we will reach to this position. Now notice that we start at position 0 on first and second substring A and B. Now second case is that we find out a match, that the value of whatever I and J is for B is actually same. If there is a match, we do this process. So whatever the way we calculated these values, so we simply do 1 plus whatever the remaining amount or whatever the remaining area is left on the substring, and that is what we are doing. So we do an addition of 1, and we again repeat the same process to finding the longest common substring. And now notice that we increased both the values of I and both the values of J. And if that is not the case, if we don't find a match, which is going to happen on most of the cases, if this happens, what we can do? Well, we can find the maximum value we can find amongst the remaining substrings. So what would be the remaining substring? Suppose the value is, this one is A of I and this one is B of J. We are at these 2 positions, we don't find a match. What we are going to do? We are simply going to check from the next value onwards whether there exists a potential match. If it does not exist, we again jump to the next value, again we check for the same thing. If we want to write it in a different manner, we can do the same thing at B over here as well. So if we are at B of J, we don't find a match over here, what we can do, we can just simply go to the next value, keep on checking with A. If we find a match, good. If we don't find a match, repeat the process. So in either case, and whatever we found, we need to return the maximum value we have found, because we need to find the maximum longest common substring. So we do an A of I or A of, and B of J plus 1, or A of I plus 1 and B of J. Whatever is the maximum that we get, we just put it in our result. Now, since we already know this, let's try to solve the recursive problem with one of our own custom example. I have taken a very small example, and you'll know soon why I'm just taking a pretty small example. So let's start with A of 0 and B of 0. So A of 0 and B of 0, the values are J and R. There is no match, which means now we have two possibilities. Either we do A of 0 and B of 1, or we do A of 1 and B of 0. So let's expand on this left subtree for now, and then we will do the remaining portion. So again, now over here again we have so what are the values? So it's J and O. So J and O, there is no match. So again we have two possibilities. We can either do A of 0 and B of 2, or we can do A of 1 and B of 1. So A of 0 and B of 2, again we found the value J and N, there is no match, so we move on. If we move on, again we do A of 0 and B of 3, but notice that B of 3 is actually a null value over here. So since there is a null value, we cannot return anything over here, so this becomes 0. We return 0. Now we still have, do we still have possibility? Yes, we have possibility over here as well, that we have the possibility to calculate A of 1 and B of 2. But now let's again elaborate on this portion. So this A of 1 and B of 1 is value O. Okay, so O is a potential match, so yeah, that's good. Both values are same, which means that we can do 1 plus over here. So now we have done 1 plus, and now we need to do whatever the longest common subsequence we found for A of 2 and B of 2. So A of 2, the value is H, B of 2, the value is N. There is no match. So because there is no match, again we move forward. So we have two options over here. We can either do A of 2 and B of 3, or we can do A of 3 and B of 2. So A of 2 and B of 3, we already know that B of 3 is null value, so we can return this as 0. So we haven't found anything on this side, and we cannot move forward. Over here, A of 3 and B of 2. So A of 3, the value is N, and B of 2, the value is also N. So over here we find a match, so the value is N, bingo, which means that we can do 1 plus over here. So the maximum of these two is actually 0. So there is nothing else to calculate. But the thing is, we already calculated a match over here. So there is 1 plus 0, which means the value for this A of 3, B of 2 is actually 1. Now because this value is 1, we again do a comparison between these two values. So 0 and 1, 1 is obviously greater, which means that the result for this A of 2, B of 2 would be 1. Now over here the value is 1, and this we already had a match, which means we need to do 1 plus whatever value we have found of A of 2 and B of 2. So the value of A of 2 and B of 2 we have found as 1. So we will, over here the value of A of 1 and B of 1 would be 1 plus 1 equals to 2. Over here we have found the value as 0, and over here the values we need to compare to with is 2. So obviously 2 is greater, so we are going to store the result of A of 0, B of 1 as 2. And now we'll need to calculate the right side of the subtree. When we calculate the right side of the subtree, we are actually calculating the values A of 1 and B of 0. Now A of 1 and B of 0 is actually, again we have two possibilities. We can either do A of 1, B of 1, or we can do A of 2 and B of 0. Now notice that this A of 1, B of 1, does this seem familiar? Yes, it does, because we have already calculated its results right across, right very next to it. Let me clean this up a bit. So we have already calculated this result, but the thing is we are still going, and will eventually keep on going, and then we will try to find the solution, and eventually we will be finding the solution as 2, because there is the longest common subsequence we have over here is of value 2. But the thing is, what are the issues with the recursive approach? Well, the issue is pretty common. The time complexity is actually 2 to the power of n. And why it is 2 to the power of n? Because at every single location we have two options, whether we can choose it or whether we cannot choose it, and pretty soon, within just few elements we had over here, I couldn't even draw the entire subtree on this side. Why? Because the values were simply growing too big, and this is the problem with the current recursive approach. But the thing is, how can we tackle this current recursive approach? Well, the reason is just right. The answer is just staring at us, and it is right over here, that because we are doing a lot of repetitive work, and somehow if we somehow have a way to store whatever the results we calculate over here, and if we just put those results, apply the logic over here, that okay, if the values are null, we return 0. If the values are same, we return whatever the value of 1 plus the I plus 1 and j plus 1. And if values are not matching at all, we simply check that what is the maximum amount we can reach to either comparing the next value on the A string or comparing the next value on the B string, and that is how we would be able to calculate the result. If we somehow store these values and use it in our approach, we would be able to compute this pretty faster and not in this exponential time. And the art of storing the values of the recursive function in some form to use it later down the way is actually called memoization. So if you want to put a definition, just like made up definition, you can create a definition like this, but it's actually really interesting to understand. And so let's see that what could be the approach. Okay, so now let's try to use memoization, and we are going to use the same example. Now between these two values, there can be three possibilities that we can have between any given elements. The possibility is either the element is null. If any of the element is null, we simply return 0. So that's base case. Either both the values are same. So if the values are same, we simply need to do 1 plus least common element of whatever we have found. So A of I plus 1 and B of j plus 1. But what this and suppose if this is A of I and B of j, so what this I plus 1 and j plus 1 represent? If we take it in a matrix, suppose this is the value we are considering, and we found that okay, there is a potential match over here between these 0 0 values. So 1 plus LCM of this would mean that whatever the value we have over here, because this would be 1, this would be 1, so whatever value we have in diagonal, if we do 1 plus that value, we would find the answer that lies at this position. So just keep this in mind, we are going to use it somewhere. And the second and the last option is that the values are different. If the values are different, we know that we need to find the maximum value for any I and j values that are different. We need to find the maximum value between I plus 1 and j, or j plus 1 and I. So amongst these two, and I and j are respected for A and B, so just keep in mind. So if we look at this, we can determine that basically, suppose for this particular element, we need to determine that what is the value for this one, and we realize that okay, the value over here is suppose x and y, so they are not matching. So we need to find the maximum value. So currently this position is 1 and this position is also 1. So what are the two possibilities we have? We could have a value at position 2 1. So position 2 1 would be the value over here. So whatever value we have over here, and second possibility we can have is position 1 2. So position 1 2 would be over here. So we need to find the maximum value amongst these two. We need to find the maximum values amongst these two in order to calculate that what should be the value for this value, this one would be. And now we have these three things. We can actually use it in our matrix. So let's start filling up the values over here. First we determine that the value and first we determine that okay, J and R for this position, the values are not matching up. If the values are not matching up, we need to see that what is the maximum value returned between these two values. The thing is, we don't know these two values yet, but keep in mind that this should be the approach. Now again over here, that the values for values are not matching up. So for this position, we need to find the maximum value between these 2 points. Again over here, the values are not matching up. So we need to find the maximum values between this and this point. The thing is, we have a null value over here. So this will always be 0. So whatever value we have stored over here, we can just impart that value over here, and that's pretty understandable. Again, if we look over here, this position, again the values of O and R are not matching. If they are not matching, we again repeat the same process. Now over here, actually we have a match. Actually this O and O matches. So if we have a match, we choose a different approach. We basically go on the right side, go on the diagonal, and whatever value we find, we do an addition with whatever value we have on the diagonal of that. And again over here, there is no match. So if there is no match, we need to find the maximum value between these two. Now we keep on repeating these things, and the only number we can calculate so far is actually this last one, the value of n, where because okay, over here both the values are same. So for this position, we can say that this would actually be 1 plus diagonal, and over here in the diagonal we have null value. So basically this would result up in 0. So we can say that so far over here the value of n would be 1. But the thing is, this is a really important property. Based on this, we can do a lot of things. So let's try to do those things over here. So currently our n is 1, and so far what are the common values we have found? Basically the common values we have found is only over here. So over here I'll just mark it as something to indicate that this is the common value. All the other values, they are not matching up apart from this 9. So now for this value, we can say that the result would be whatever we have over here and over here, but this is null, this is 0. So we can just impart this one. Again we can do the same thing, and again we can do the same thing. Now even for this particular position, we need to find the maximum value between this point and this point. But the thing is, over here the value is null, so nothing exists over here, and this value is 1. So again we can impart the same thing over here, and same happens for this position. So we have filled these values so far. Based on these values, okay, now over here the values are not matching up. If the values are not matching up, we do maximum of next element or bottom element. So both are 1, so we can again do 1. Now at this particular position, and again over here we need to do maximum of this and this. So again we do 1. But now for this particular position, we still have a match between this O and O, which means we need to do a diagonal plus 1. So if we do diagonal plus 1, in the diagonal the value we have is 1. So if we do diagonal plus 1, we actually get the value as 2. So this becomes our 2. And now for this position, we need to do a maximum of these two values. So that's obviously 2. Again for this position, we need to do maximum of these two values. Again the value is 2. And for this position, we need to do maximum of these two values. So the answer is 2. Now at the end, we can simply return whatever we found at 0th position, and this would provide us the maximum longest common substring we find. And we are able to calculate this because we actually stored some of the values in memoization. We went over the matrix again. We implied the logic we have defined over here, that if the value is null, return 0. If the values are same, do 1 plus diagonal. If the values are different, take the maximum value of either next element or bottom element. And that enables us to find the answer of this problem, and actually and times m, uh, and using that we can actually find the solution of this problem in big O of n times m complexity. Why we are able to use this big O of n times m? Because we need some time to create this array, this matrix, and once we have this 2D matrix filled up, we just need to iterate over it and eventually we would find our answer. So very important property to understand, and very easily we can do this thing. The thing is, notice over here that we are still doing bunch of things, and we are doing a lot of repetitive work, because during the first iteration we don't even have any values to compare to. So now what can we do? So again, the beautiful words dynamic programming can be used over here, and dynamic programming can actually solve this problem. Now suppose in the dynamic programming we are again considering the same problems, and what should be the index value? It would be 0 1 2 3 and 0 1 2. The thing is, notice over here that we actually create a matrix with one value addition for both these two lengths. So let's see that what the values would be. So over here this would be John and this would be Ron. Now for this additional values 3 and 4, we can actually say that this value is basically null and this value is also null, because the string ends at this position. So once the string ends, we can actually, and we know that if we encounter the null value at any moment, the value for that portion is actually becomes 0. So if this is 0, we can already pre-fill these values. So let's do that. So this would be all these values would be 0 and all these values would be 0. Now we have all these values as 0. We can start filling up our matrix, and using that we will be able to compute things pretty fast. So let's see that how can we start filling up our matrix. By the way, we can fill up our matrix in two ways. We can either start at the bottom position and go up and side, so eventually we will reach over here, or we can actually start at this position and eventually we will reach at the end. So it's up to us that what approach we want to consider. I'm just starting at the bottom and now we are here. That's a bad pun, but okay. So this particular position, we know that the value, there is a match. So if there is a match between n and n, we need to do 1 plus diagonal. Diagonal is 0, so we can fill up this value as 1. Now for this particular value, there is no match. We need to do whatever the maximum of diagonal, so the value becomes 1. Over here again we need to do maximum of diagonal, so the value becomes 1, again maximum. And on this particular row, column 3, we again do we keep on checking the maximum of two values, and we just provide those values. Now at this O and O there is a match, so this point there is a match, but before that there is no match. So over here again we check the maximum of next adjacent values, so the value becomes 1. Again maximum of adjacent values, the value becomes 1. Over here we see a match, so whenever we see a match we do 1 plus diagonal. So 1 plus diagonal is actually 2, which means we can just put the value 2 over here. Now since we have 2 over here, this would become actually the maximum of adjacents, because there is a mismatch between R and O. So maximum of adjacents is 2, and again the maximum of adjacents between these two values is 2. So at the end we just find the maximum value, and that is 2. And see our solution, how beautiful it looks. We were able to calculate everything because we had this original initial case. Using this initial case, we were able to compute all the values. And over here, because we had like these n's matching, we were able to get 1, because 1 plus diagonal. But even if this was not a match, this was something else, basically we could have filled this value with 0 as well, and then again we will subsequently move forward with our solution. I hope that this this dynamic programming solution makes sense. You are able to understand that how we come up with, why we created this additional column and row, and treating them as a base case, we start filling up our matrix. And basically this problem was originally NP hard problem. What NP hard means is that the problem is runs in non-polynomial time, but using the smartness of computer, and because we are storing the values and we are keeping track of it, we are actually able to solve it in n times m time complexity. So even for data power dynamic programming approach, the time complexity would be big O of n times m, and the space complexity would also be big O of n times m, because we need to create an additional matrix to store all these values. So first of all, we'll create a matrix to store the values. Now we will create two loops to iterate over the matrix. We will start at the bottom right position and eventually we will end up at the 0 0 position. So now inside the loop we have two conditions. First condition is if both values are matching. So if both values matches, we need to do 1 plus diagonal. So okay, now we have taken care of one case. Second case is that both values are different. So if both values are different, for a matrix of I and j would be we need to select the maximum value out of the adjacent values, and yeah, I think this should be it. This should be our logic, and let's try to return the position, return whatever value we found at the first position. And let's try to run the code. Okay, as expected there are some errors. Oh, okay, our solution seems to be working. Let's try to submit this. And yeah, our solution works pretty fast. It is, comparing to other, it's pretty faster. And I know that this so far has been pretty long video, so I apologize for that. I try to make small videos, but the thing is I'm not good at explaining briefly, so I'll try to improve upon that. But our aim is to understand as many concepts as we can, and clear FAANG interviews. So yeah, hope you like the video, and I will be posting the solution in the comments so you can collect it from there. Thank you.